Welcome to today's Explainer. You know, it's pretty mind-boggling when you think about it. Every single time you click a link, a microscopic laser blinks millions of times per second just to shoot that data across the globe. I'm so thrilled you're here with us today. If you're the kind of person fascinated by how things work at the absolute fundamental limits of reality, well, you're in the exact right place. Today, we're demystifying the physical limits of internet speed, and we're going to explore exactly how brilliant minds are manipulating the very physics of light to make our global networks faster than ever before. All right, let's dive straight into a massive question, one that literally keeps engineers awake at night. How in the world do we force the internet's lasers to flash faster without completely breaking the signal? Think about it. Every single email, video stream, or data packet you request gets transmitted as a literal flash of light through fiber optic cables. So, to get faster internet, those lasers need to blink on and off at speeds that almost defy logic. But, as we'll see, when you push a laser too fast, physics pushes back.
So here is our roadmap for today. 1. The optical speed limit. 2. Inside the laser cavity. 3. The signal hack, which is current shaping. 4. The hardware hack, utilizing coupled cavities. And finally, 5. The future of networks.
Let's kick things off with part 1, the optical speed limit.
First, we really need to grasp the macro-level problem we're facing with today's massive global data demands. Our modern networks rely heavily on cost-effective, directly modulated semiconductor lasers, specifically VCSELs or vertical cavity surface emitting lasers. Now, direct modulation just means we encode information by rapidly changing the electrical current pumped into the laser. But here's the kicker. Researchers have found that standard VCSELs hit a stubborn physical ceiling right around 30 gigahertz. This 30 gigahertz wall exists mainly because of hard limits on how much heat, electrical resistance, and energy these materials can handle before the signal just degrades completely. If we actually want to push past 100 gigabits per second to handle our exponentially growing network traffic, we can't just keep turning the dial up. We absolutely need a fundamental breakthrough.
Moving right along to part 2, inside the laser cavity. So to figure out how to break through that 30 gigahertz wall, we need to zoom way into the microscopic world. Inside the laser, we've basically got two main players interacting: photons, which are the particles of light, and the carrier density, which are the excited electrons. When we drive a laser too fast, we smash into a critical bottleneck known as intersymbol interference, or ISI. This happens when rapid sequences of information symbols start to overlap. And what's absolutely fascinating here is this concept of dynamical memory. See, even if the visible light output returns to normal after a pulse, the unobservable carrier density, those internal electrons, might not have settled down yet. The laser physically remembers the previous bit, and that leftover energy, it completely corrupts the next bit you try to send. Imagine feeding the laser with a traditional square-like driving current. We are basically slamming it with ones and zeros. When we look at the resulting photon density, or the actual light output, we get these jagged, violent peaks right after every upward jump. Those peaks are called relaxation oscillations. The output physically rings at its characteristic frequency. Now, at slower speeds, this is totally fine, no problem at all. But at ultra-high speeds, those wild oscillations bleed right into the next bit of data, completely ruining the signal. It helps to think of the laser like a physical bell. If you strike a bell just once, you get a clear, distinct ring that eventually fades out, right? But what if you strike that bell with a heavy hammer over and over again as fast as you possibly can? The sound waves overlap. Those distinct rings just merge into this continuous, chaotic, muddy noise. Plus, you probably just gave the bell a massive headache. Well, that is exactly what happens to our laser's light pulses when we hit it with a square wave too rapidly. The light just muddies into intersymbol interference.
Which brings us to part 3, the signal hack, current shaping. So how exactly do we fix this money noise? Well, researchers Illing and Kennel realized something brilliant. You don't necessarily have to change the physical laser device to solve this. You can actually use a software hack. The old way relies on slamming the laser with those harsh, square-wave currents, switching violently from off to on. But the new way? It uses time-optimized, smoothly shaped currents. Instead of a blunt square block of energy, they feed the laser continuous, mathematically calculated shapes with very specific rise times. By carefully designing the input signal, they can quite literally control the chaos inside the laser.
It is essentially a mathematical feed-forward solution. Here's how it works. Step 1. They defined exactly what they want the final light output to look like. We're talking a perfect, clean pulse with absolutely no ringing. Step 2. They take the incredibly complex differential rate equations that govern the laser's physics, and they solve them backward. Then, step 3. This reverse math generates the absolute optimal driving electrical current. By meticulously controlling the state-space trajectory, they smoothly connect the off-state to the on-state, entirely bypassing those wild relaxation oscillations.
As the researchers perfectly summarized, this technique allows for the suppression of relaxation oscillations and the avoidance of dynamical memory. By mathematically shaping that current, they ensure that at the end of every single bit of data, both the photon density and the hidden carrier density are forced back to a known, stable fixed point. The laser completely forgets the previous bit. Zero memory, zero overlapping, and zero muddy noise. It's just an incredibly elegant software solution to a deeply physical problem.
All right, moving on to part 4, the hardware hack, coupled cavities.
But what if you do want to change the physical laser? That brings us to an approach pioneered by Ahmet and colleagues, who came at the problem from the exact opposite direction. By redesigning the physical laser itself, they created a nanophotonic device that looks almost like a high-tech microscopic flower. This is a hexagonal transverse coupled cavity V-cell. What they've done is integrate the primary central laser cavity with multiple surrounding lateral cavities, usually 4 or 6 of them, coupled together through oxidized apertures. It is a seriously astonishing piece of microscopic engineering.
When that central laser fires, the light doesn't just shoot straight up. It actually travels sideways into these surrounding lateral cavities too. These extra cavities act kind of like traps. They force the light to travel perpendicularly, which drastically slows it down. This slow light then reflects back and feeds directly into the main central cavity. And this direct, anti-phase optical feedback induces a remarkably powerful phenomenon called photon-photon resonance, or PPR.
By utilizing these multiple lateral cavities, the device manages to accumulate a massive amount of slow light feedback, even if the coupling from any single cavity is relatively weak. This anti-phase coupling creates that photon-photon resonance at incredibly high frequencies. On top of that, testing showed that having 4 or 6 cavities actually suppresses what's known as low-frequency relative intensity noise. So not only does the laser pulse wave faster, but it also remains highly stable and remarkably quiet, completely avoiding the chaotic instability that usually plagues lasers when they're pushed to their absolute physical limits.
And that hardware hack leads us to a truly staggering number: 170 gigahertz. Remember that 30 gigahertz wall we were talking about earlier? By utilizing 4 to 6 transverse coupled cavities and harnessing that photon-photon resonance, researchers predict they can push the 3 decibel modulation bandwidth all the way up to 170 gigahertz. That is nearly a 6-fold increase in raw physical speed capability. It literally blasts right through the traditional ceilings of optical physics.
Finally, let's wrap up with part 5, the future of networks.
So why do these microscopic hacks actually matter to you and me? Well, we're basically looking at 2 sides of the same incredible coin here. The philosophy of current shaping is to optimize the input signal using advanced electronics and math, which beautifully eliminates dynamical memory and signal noise. Meanwhile, the philosophy of coupled cavities is to completely redesign the physical device using nanophotonic slow light feedback, resulting in a massive bandwidth boost. Whether we attack the speed limit through advanced software and signal processing or through revolutionary hardware geometry, we are proving that the old physical limits of lasers can, in fact, be outsmarted.
The real-world impact of these breakthroughs is going to be absolutely monumental. When we can manufacture lasers that reliably modulate at these ultra-high frequencies without corrupting their own signals, we unlock the true potential of tomorrow's infrastructure. We're talking about the very backbone of 5G and the upcoming 6G mobile networks. We're talking about clearing out the data bottlenecks inside supercomputers. We'll see next-generation, hyperscale data centers. Even high-end autonomous sensor systems that rely on instant data processing are going to be vastly accelerated by these high-performance lasers.
Which leaves us with this final, truly provocative thought. For a long time, we thought 30 gigahertz was a hard physical wall. But human ingenuity, through both brilliant math and cutting-edge nanophotonics, completely shattered it, reaching toward an unbelievable 170 gigahertz. If we can manipulate the very memory of electrons, and if we can trap light in microscopic hexagonal petals just to push our infrastructure this far, what exactly comes next for the absolute limits of light? Thank you so much for joining me on today's Explainer. Keep questioning, keep learning, and I'll catch you next time.